We start where we stopped yesterday. We have now a concept of how a spectrograph should look like to do our radio velocity measurements. And we want to do precise or even extremely precise radio velocity measurements. So we have to take into account several aspects, how to get there. And that's what I will try to tell you today, how to get there. And I would like to just summarize this in the so-called HARPS approach, because there have been instruments before HARPS, 51 Pegasi b, first exoplanet around solar-like stars, was discovered using the LOD spectrograph, a medium, 50,000 resolution spectrograph, relatively bad sampling, it was not stabilized, and so on and so on. It went well, but the precision at that time was of the order of 15 meters per second with that spectrograph. There were other spectrographs at that time which were better than that. The Canadians, Walker et al., or Americans, they were doing, Butler, for example, there is a paper, 93, if I'm not wrong, or 96. They were doing already 3 meters per second. So they were doing better. Okay, maybe not 3 meters per second, but better than LOD. And at some point there was a call by ESO, and we had to produce, we were asked to build an instrument which would be able to do 1 meter per second. So at least about 10 times better than what we were doing in Geneva. Okay, we were not doing better than 10 meters per second in 99 when there was this call. So we had to decide about an approach, how to get from, let's say, 10 meters per second level to 1 meter per second level. And this within 3 years, because we were given 3 years to build it in exchange of 100 nights per year of observations for 5 years. So 500 nights, really a nice award, but for every month of delay, we would have been punished by 1 month less observations. So it was really important that we build this instrument in the 3 years, because the main goal was the science program. Okay, it was not just for fun or just to show that we are better than the others. We wanted to do a scientific program, and the scientific program was to search for, let's say, Earth mass planets. That was the scientific program. That was the goal. And for this, you needed a 1 meter per second instrument. And that was the approach. You will see, I will go through these different elements, but basically start from experience. This was the LOD Corelli spectrograph. Try to see what we can get with this one, where are the limits, and from there, try to improve the detector, the mechanical mounts, the illumination, the stability of the spectrograph, and this with a wonderful team, of course, otherwise you go nowhere. And the extrapolation of the HARPS approach is espresso. Espresso is the same philosophy. There is no reason why espresso should be better than HARPS, because we had exactly the same approach, with the very, very similar solutions. The only difference are the telescope size and the resolving power, which make a difference. They make a difference. I don't remember, Sourav maybe knows better. There was this decadal survey I think it was 2007 or so. It was at the Kepler conference in Cambridge. And the decadal survey just stated, it was an evidence that there were not enough radio velocity spectrographs. And HARPS, I think, if I'm not wrong, was taken as an example of what should be done worldwide in the next decade to get there. And this work has been done. This work has been done, and there are now plenty of instruments doing as good as HARPS, okay, around the world. You heard already by Sourav about HPF and NUID. There was Kermenes in Calarto in Spain. Here in India, Paras-2, which is, if I'm not wrong, the highest resolution optical spectrograph in Asia. Okay, there is the KPF, which had first light a few years ago on the Keck telescope. So you have these, and there are many more. I mean, HARPS has been copied twice since. There is HARPS North on the Italian TNG telescope, La Palma, and there will be a second northwest because it's just next to the HARPS North. There is a HARPS 3 instrument which will do a blind search for Earth-like planets in our solar neighborhood. And then you have the infrared versions of HARPS, but there are other infrared instruments, for example, IRD on Subaru, and Espresso Maroon X Express here on 4-meter class telescopes, or Maroon X on an 8-meter telescope. So there are now quite a number, but maybe you have noted they are all somehow in vacuum and stabilized. Okay, this has become common practice or good practice to do stabilized instruments. That was not the case before. IRIS on the Keck was a very good instrument. UBS is a very good instrument at the VLT, but they were not stabilized. The approach was different. Let's try to do the most efficient and the highest resolution instrument, and then we try to get a better precision. Here, the paradigm was inverted. Let's try to do upfront a best precision instrument. For this, we need resolution, we need efficiency, but the goal is the precision. I've chosen this as an example of what is the state of the art. It's Maroon X paper, okay, on the Barnard star. You heard already about that. I show this example because here you can see several aspects. First of all, the level of precision you can get. Just checking here, okay, 30 centimeters per second with Maroon X, 25 centimeters per second with Espresso. That's the state of the art. So that's what we can do today. It's best what we can do, but we can do it. For planets of a fraction of the Earth's mass, at least the M sinus I. Okay, we do not know whether the sinus I is 1 or not, but the signal corresponds to a fraction of an Earth's mass. Okay, on a relatively short orbit. So that's the first. But there is a second point. These are the raw radio velocities. And you see here that the stellar contribution is much higher than the planetary radio velocity change. So you have to cope with that. And for this, you need to be sure that the instrument is not introducing bad things. Otherwise, you cannot combine different instruments. You need enough photons. Otherwise, you cannot measure the stellar signal. You will measure stellar noise. And you need to model that. Okay, so you need to develop, you need to understand stellar effects and to be able to model them and have techniques to model them. So that's all the things you can say. There is an additional one here. Look at the difference in RMS between the blue and the red arm of Maroon X. It's not exactly the same. And it's not photon noise. It's not photon noise. So why? I do not know, but this is just to show that you are not 100% sure get rid of all the instrumental effects. So if you want to go to Earth's mass, a real Earth analogs, you still have to be careful of what you do with the instrument. Okay, I like this picture here. I think this was shown by Deborah at EPRV 1 or 2. I very much like this picture here because this is really what we are doing, okay? We have to nail down every problem one after the other. We just see the biggest problem first. We try to solve this one, but then we discover a little bit smaller problem. And so we try to get down one after the other. Of course, there is the square root of that. But anyway, okay, so we have to cope with different contributions. So this is what we are working on for the instrument, but also for the stellar effects. There we are now, in many cases, we are limited by stellar activity or other effects, and we have to understand how to cope with that. And what I also said yesterday, we should not understand that to do this work well, we should have enough photons. And so we have, this is a limitation for space-based projects. That's still an advantage of ground-based spectrograph with respect to space-based missions. And that's why I asked yesterday the question and you answered. I mean, I somehow knew it, but I think one has to realize that there is no chance to put a 40-meter telescope in space. It would cost 100 billion, or I don't know whether this will be sufficient, at least today. This can only be done from ground. There is a factor 500 per square meter of collecting area between ground-based project and space-based project, about 500. Maybe 1,000 can be less, but that's the level. So here we have, there is a clear advantage with respect to space, and we can do it from ground because the atmosphere is not too much annoying in the optical. And, but sometimes people forget that we need photons. Okay, so that's the approach. And before entering in all the instrumental effect that actually hurt the measurement, I want to give here a few definitions. I insisted on that. I wrote an article here about EPRVs, and I tried to give here a definition of words that are commonly used, but we do not all understand the same with that. So I made an effort to give my definition of that. You may agree or not, but at least that's what I will use throughout my presentation here. When I talk about stability, then this is really, let's say, mechanical or material, okay? So how stable is something? A spectrograph. This means how stable is the spectrum projected, or how stable is the spectrum when projected on the detector? Is it moving or not? Okay. How stable is the mechanics or thermally? I will use the stability for this. I won't use the stability for the measurement. Stability is a characteristic of the instrument, not of the measurement. While precision, that's what I would use to call the internal precision, or let's say the fundamental precision, the one which is limited by pure physics. Okay, in our case, the aim is to get down, to nail down the measurement to the photon noise precision. That's the best we can do in optical astronomy. It's go down to the measurement, which is the observable precision limited only by the photon noise, by the counting of the photons and the fact that they are discrete. Repeatability and accuracy are two characteristics of the measurement. If I do a measurement today, I get a certain value, will be affected by photo noise, but also by instrumental noise or other errors. So the ability to repeat the measurement is the repeatability. Okay, if I do it tomorrow or in 5 minutes or whatever, I should get the same value within the precision, but I don't. I will not probably. So that's what I call the repeatability of my measure. How repeatable it is. Accuracy is the ability of not only having a repeatable measurement, but this measurement is as close as possible to the truth, to the real value of the observable, which if I was God, I would be able to measure this without an instrument, okay? That's the real value. And the question is, how close can I get it to this value with my instrument? That's the accuracy. And in order to get accuracy, I need to go through a calibration process, because my measurement is a projection of the truth into a measurement system, a measurement instrument. And this measurement instrument needs to be calibrated with a reference before I can get the number of this measurement. Okay? So what are the limits? In summary, as I said, so affecting the fundamental precision, of course, it's the telescope size, the spectrograph efficiency, resolving power, you will see that in a moment, how I extract my ability to extract information or the signal from the data. What will affect the stability? Changes of the instrumental profile. So my line, is it changing because the astrophysical source is changing or because my instrument is changing? Okay, illumination. How do I bring the light into the spectrograph? Optothermomechanical effects, okay, which will affect the stability of the instrument itself and make the spectrum move. Detector noise effects and so on. Repeatability and accuracy, they belong a little bit together, okay, because you have to do some calibration at some point. So as I said, the difference is just the offset, the bias, the long-term bias, if there is a systematic effect. But basically you need to know when I do a calibration, for how long is this calibration applicable to my instrument? Is it valid for today? Or can I apply the same calibration also for tomorrow? Okay? I have to measure possible drifts. So if there might be drifts, there might be modal noise. I might have problems with extracting the information from my signal, bad sampling or things like that. If I undersample my signal, I can't extract it. Contamination, external sources, and so on. Here, the accuracy, you will see, it's how good are my calibration sources, how good is my calibration method, and how good can I remove residual instrumental signatures from my data. And then the stellar noise that you learned already with Sourav today, okay, from P modes, granulation, activity, everything which is linked to rotation, spots, okay, and convection, suppression, things like that. Okay, there is a lot of sources. I won't talk about this latter point today. Fundamental precision. There is a paper by Butler, 93, but there is also a paper by François Bouchy, 2001, where we try to give a formula of what is the information content. How precise in grid velocity can I get if I do everything right? Okay, photo noise limit. I tried to recompute that in some analytical way, assuming that the line profile is Gaussian, okay, which is not too wrong. And you can estimate the error that you do. Here, x is a pixel, but you can convert easily x in radial velocity once you know the calibration of your spectrograph. How big is the error that we do in the photocenter, okay, in the position of the line? Because that's what radial velocity is about, measuring the position of the line. You can define it by doing a fit. You can define by just computing the photocenter. It doesn't matter too much. You want to have the position of this line, and the information is everywhere but in the continuum. As you already said this morning, the information is here in the derivative, in the slope. So the error will depend here on the width of the line, which is affected by the intrinsic line width and by the resolving power. So we want to have the highest possible resolving power in order to make the error as small as possible. But of course, at some point, since they add quadratically with the intrinsic line width, it won't help anymore. You won't gain anything in terms of precision because you will be limited by the intrinsic line. So there is this effect here. That's the equivalent exposure time you need to get a fixed error in radial velocity as a function of resolving power. And here you see, I don't remember what is, yeah, okay. So it's for different rotational velocities of the star, because this will broaden your intrinsic line width. So if it's rotationally broadened, then you flatten much earlier. But let's focus on this. This is a typical, let's say, quiet, non-rotating solar type star. You increase, so you reduce the exposure time by many factors when going to high resolution or to high resolving power. So that's 100,000, and you still increase it. But here it starts to flatten, and that's the famous 100,000. That's why we aim at 100,000 at least. Same here. This time I have the error as a function of resolving power, which of course, okay, you can either fix the error and compute and determine the exposure time you need, or you fix the exposure time, you look at the radial velocity precision you get. Is this concept clear? Okay. You see here, the signal to noise, when you go to cosmologists, they always talk about signal to noise. They only care about signal to noise. But actually, we do not care about signal to noise only, because our signal is here, is this depth here, and this width. Okay, the deeper and the steeper, the better precision we get. And our signal is that. And our noise is given by, let's say, the photon statistic in the continuum, yes. But the signal is the line. So I will go through a few instrumental effects here. I hope you will not be too much afraid. A spoiler, or I already did the spoiler, we get to 20 centimeters per second eventually, okay? But still, if you knew all these before building HARPS, probably we wouldn't have built it. So there are illumination effects, as I said, spectrograph stability effects, detector effects. How did we build the spectrograph? As you can see here, that's a picture of HARPS. What you see here is the vacuum vessel. This was one of the first decisions we made in 2000 to put the spectrograph in vacuum and to stabilize the temperature. But the vacuum vessel was actually the most criticized. People were telling us it's much too expensive. Why do you do the spectrograph in vacuum? And the reason for that is because if you don't do that, that's the level of stability of your spectrum you get. Okay? If, like yesterday, there was a thunderstorm, okay, the pressure, the ambient pressure changes by several millibars when a depression or a high pressure zone passes by. 1 millibar external pressure change, if you don't put the spectrograph in vacuum, will move the spectrum by 100 meters per second. 1 Kelvin temperature change will move your spectrum on the detector by 100 meters per second. So 1,000 times more than what you want actually aim. So why should you live with that? I mean, you're building a car which is able, a super fast car which is able to drive at a speed of 300 kilometers per hour, but you accept to have a driving wheel which has a play. So you're driving like that at 300 kilometers per hour, and you have a play in the system, and you actually can't control the car. So let's remove all zero-order effects. Let's make the spectrum stay stable on the detector. That's the basic philosophy, and that's what we did here. Put in vacuum, try to stabilize to a reasonable level. Reasonable was, at that time for us, millikelvin. That's something that you almost easily get. And putting in vacuum is not so difficult. There is no moving element in the spectrograph. They are all balled down. There is no screw, no alignment screw, zero alignment screw. Everything is done by machining. Everything is done by shimming. That's the philosophy. And I think that's something that has become standard to do the spectrograph like you don't need alignment screws once it's aligned. I just show you also the Eshel grading. This was a novelty, UBS and of HARPS, is to go for a monolithic Eshel grading. So this is an Eshel grading of 80 centimeters. There was no such grading in the late 90s when they built UBS. So they decided to try to replicate 2 smaller gradings on a bigger monolithic zero-dur block. Okay, that's Richardson Grading Laboratory who's doing that. Okay, so you take 2 submasters with the grading on the top here. You align them very precisely. Then you put a resin on the top. By the way, what I didn't say is here, these submasters are coated with an aluminum coating. Then they put this resin on the top, and they just glue the zero-dur blank on the top of the 2. Sorry, I made a change in my, so it should be on the top of the 2 here, okay, and not below. The resin sticks on the aluminum and takes the shape of the grating, and what is left is the zero-dur block with a replicated grating on the top. And the aluminum coating, which actually went away from the submasters. So you recover the aluminum coating. So you have an aluminum coated grating of large dimension. I'm showing that as an example. This is an extremely expensive piece of optics. It's about 6 times more expensive. No, let's say 4 times more expensive compared to if you just bought two individuals blocks and put them on a mechanical mount. But we decided to go to that because we wanted to avoid any possible instability source. And this has been done for all the other optomechanical systems. Yeah, you know about maybe this effect here. Okay, let's suppose we have a slit spectrograph. You remember yesterday, I explained that a spectrograph is nothing else as an imager, but it's imaging the slit on the detector, and the image of the detector depends on the wavelength. But what you see is the image of the slit. If you illuminate a slit spectrograph with a target which is moving across the slit, so it's changing the illumination of the slit, on the detector, you will see a moving spectral line because it's the image of the slit. So the slit image will move, and you may confuse that with a radial velocity change. That's why a radial velocity spectrograph today, they are all fiber fed. Because when you inject the star into a fiber, okay, and you add a double scrambler, which I will explain later, even if you move the target on the fiber, this will scramble out the light distribution. So it will make it uniform, and you will get always the same image of the fiber slit or the fiber on the detector. So no effect of illumination. That's simulations. You can go back here if you want. Okay, that's the fiber tip. If you inject the light, a point light source, not in the center, but a little bit off center, then at the output, you won't get an exactly uniform distribution of the light. You will get here a memory, okay, of the position of the source. That's incomplete scrambling. If you do the same in the far field, I don't know whether you have done lab with lasers and fibers, but if you take a waveguide, or a fiber is a waveguide, and you inject the laser with an angle, so not on axis, but with a certain angle, let's say 20 degrees, what will you see at the output of the fiber? If you project the light at the output of the fiber on a wall, I inject a laser in a fiber with a 30-degree angle, 20. What will I see at the output? Sorry? A little bit louder, please. So you say that you will see a beam going out with a bigger angle. Not exactly the case. It's shown here, actually, if you manage to interpret this. Yeah, actually, only few modes will be illuminated. But here we can even, we are not yet at the level of the modes. We can even think in geometrical terms. Imagine a tube, just a big tube, and you send a beam into the tube with a given angle. What will happen with the beam? It will be reflected on the tube wall with which angle? Yeah, we are within the critical angle, so it will be reflected. Okay, if I inject it with 20 degrees, what will be the reflection in the tube wall? It will be 20 degrees. And then it will go to the other side, and what will happen? Sorry? Yeah, it's always total refraction. So the input angle is equal to the output angle. So the beam will do like that, correct? and it will exit at exactly the same angle. But because of the cylindrical shape, it might turn around. So you will have one beam going in at 20 degrees, but at the exit, you will have a ring, a cone, a ring of 20 degrees. That's what is shown here. Okay, that's the far field. It's the projection, it's the angular distribution. You go in with one single beam, laser, but at the exit, you will have a ring. But you will have no light in the middle. You will not have a uniform cone. You will have a ring. So the far field of a waveguide here, a fiber, is a waveguide, nothing else, is not scrambled. Okay, you keep the memory of the angle, of the input angle. There is no scrambling, and that's why we have to do several tricks here. I show you also the effect. Okay, so that are again simulations. If you put then some stress on the fiber, you get even worse situations here. And if you now project, if you have a pupil of the spectrograph, if you illuminate your spectrograph, not with a cone, if you fill your lenses and your echelon grading, not in a uniform way, but with a ring of illumination, then your PSF, your line, will change, the shape from that to that, or vice versa. The line shape will change if you don't illuminate your spectrograph always the same way. That's the far field effect. This is the near field effect. Both are dramatic for radio velocity measurements because you want to measure the centroid of this guy here. And you see that the centroid changes completely. Okay, that's what we measured on HARPS. We had circular fibers which are supposed to scramble, but when we were observing the radio velocity along the echelon orders to the right and to the left, since the PSF is asymmetric, when we were observing radio velocity changes as a function of the right-left asymmetry. This was a sign for us that apparently we were injecting the light not always in the same way. This is actually, if you would plot here the seeing as a function of effect, you would see that this is a seeing effect. Sometimes we were focusing a very narrow star on the fiber, sometimes we were filling the fiber. This translated into a far field variation, and this translated into a radio velocity effect with a circular fiber. This is the centroid effect. If you change the pupil illumination by a large amount, you have here hundreds of meters of effect, okay, along the orders from right to left in a spectrum. And this curve is not symmetric, and it will not average out, and you will get the effect that we measured on HARPS when the seeing is changing. So is there hope? Yes. And the first element of resolution of the problem is that instead of you using circular fibers, which have some kind of this memory effect because of the symmetry, you break the symmetry by using octagonal fiber, hexagonal fiber, even fiber with 7, I don't know in English, 7 is how much? Anyway, or quadratic, rectangular fibers. You can use whatever you want. Look at the uniformity of the illumination. These fibers were illuminated with a point-like source, but at the output, that's a real picture, you get a perfectly uniform illumination. That's scrambling, okay? but they won't scramble the far field. Remember, they will only scramble the near field. Fibers only scramble the near field, not the angle of distribution. What should we do? What would you do? Okay, you may have to make sure that your light uniformity on the tip of the fiber is uniform, perfect. But also you need a uniform and stable angular distribution. Your cone, your light cone, must be perfectly stable in your spectrograph. What do you do? What would you do? Sorry? And how would you do that? So one after the other. How would you do that? So sorry, a little bit louder because you would put the first at the, yeah? Yeah, but how do you get the far field scrambled? You do it one after the other, but how do you get the far field scrambled? You convert the far field into near field because the near field is scrambled. Okay, good. So you have a bad scrambled, okay, that's still the circular fiber here, okay? You scramble first the near field here, then you double scramble, and then you re-scramble the far field. Now, these simulations here don't show a very good scrambling because in this simulation we use circular fibers. If you use this simulation octagonal fibers, then you get here a perfect uniform illumination of the far field and of the near field, of both. That's the double scramble. So the double scramble is no magic. It's just an assembly of an octagonal fiber or something else, a hexagonal fiber, whatever you want, something that scrambles very well the near field, then makes an image of the fiber tip onto the pupil and an image of the pupil, so the far field, onto the fiber tip of the next fiber. Here, that's the double scramble. You invert far field and near field, and this fiber here will take care of the far field scrambling, which has become near field in the meantime. And this works. This works perfectly. I mean, perfectly. To the extent I could measure. That's a measurement on espresso. We did that. Okay, double scramble with octagonal fibers. And what I did in laboratory, I put a calibration source and I measured the position of the lines of the calibration source on the detector. Let's say a radial velocity of the calibration source. I move the point-like source on the fiber tip at the entrance, and I measure the radial velocity here. And that's about 10 centimeters per second, okay? So I measure, I move the source from the edge to the other edge here, from -1 to 1, okay? I moved across all the fiber, and you basically do not see an effect at the level bigger than 10 centimeters per second. And what is here is probably some residual or some additional noise because it's a double difference. I use the second fiber to track instrumental drift, potential instrumental drift. So there are a lot of differences here, but still, okay, this demonstrates that the double scramble, at least in the visible, helps a lot to remove this kind of effects. That's not the same as modal noise. Modal noise is a level, let's say a geometrical level below geometric or scrambling or geometrical scrambling. Geometrical scrambling, you can explain it by ray tracing. You don't need any Fourier optics, any electromagnetic field analysis. Okay, you just can trace the rays and you understand what happened. When the wavelength becomes comparable to the waveguide, then you get standing waves. Then you get modes, discrete modes. You see them, for example, when you see speckles in a laser. Okay, that's how it would look like, for example, if you take an image of the fiber or the far field. Again, you would see intensity variations here, which are produced by the overlapping of the different modes, which are transmitted by the waveguide. This becomes very critical when the wavelength becomes comparable to the waveguide. So the longer wavelengths you go, the less modes you have, the course of this distribution, and you can see that this is a almost static distribution because it depends on the waveguide. It's not a characteristic of the light, it's characteristic of the guide, the waveguide. And so as long as you don't change it, they will remain stable. But if you heat the fiber a little bit up, or you bend it a little bit, these modes will change. Now, if you manage to make them change very rapidly, you can hope averaging this out. That's modal noise scrambling. If you don't, then they will evolve very slowly and they will change your distribution of light and the rate velocity you measure eventually. So they have the same impact on the rate velocity, on the IP, as geometrical or non-uniformities of the light distribution. So you have to make sure to populate all the modes of the fiber. That's the first step. This is done, for example, in the NIRP spectrometer. They actively move around the target on the fiber tip to make sure that the light enters as many modes as possible. That's the first step. Okay, then you have to mix the modes if possible, because you still have the problem of the far field and near field and so on. So some static scrambling is still useful. And then you have to somehow make these modes evolve with time, and time scales which are much faster than the exposure time, to make sure that you average out during the exposure. This can be done, for example, with stretching the fiber, bending the fiber, shaking the fiber. The most effective we saw is that you stretch it, because by stretching slightly the fiber, you really make the modes evolve very quickly without producing focal ratio degradation. I mean, light losses in the fiber. If you bend it, you may have light losses in the fiber. So stretching seems to be more effective, but you have to go for one of these. And then what Sourav already mentioned is, if you want, to be honest, we haven't tested it yet on Sky. There will be iLocator coming soon, hopefully. A monomode, high-resolution spectrograph. We will eventually know whether this is the right solution, because if you have only one mode, then the only changes you can have are intensity changes. But that's not a problem, okay? Because it's uniform, one mode is uniform. So going for, in the infrared, probably, going for monomode spectrograph will be the solution to this problem of modal noise. But for this, you need to inject the light into the monomode fiber. That means that you will need adaptive optic system, extreme adaptive optic system, if you don't want to lose light. Detector problems. Yeah, maybe I should not have started with that because espresso doesn't have this problem. So a CCD, you know how a CCD works? Charge, okay, coupled device. Okay, so you transfer so you acquire, you expose, you get the electrons into the pixels, but then you have a few amplifiers at the corners. So you have to transfer the electrons, avoiding that they mix up, okay, with the clocks. You clock the pixel in a way that you can transfer the electrons to the serial register, and then you transfer them again, and you read every pixel or the electrons coming from any of the pixels one after the other. You read them out one after the other. During this transfer, there might be electrons going from one pixel into the neighboring pixel. They are somehow lost, okay, or forgotten during a transfer. This is a very, very tiny fraction of electrons. Normally, you count them by number of nines. So for example, the CT, the charge transfer efficiency, is given in 6 nines. So 0.999999 electrons of one part in a million of the electrons will be forgotten in the next pixel. But when you transfer this 4,000 times, that's the size of a 4K, 4,000 pixels, or 9,000 times, like in the bigger, or 10,000, the bigger CCDs, then you have these numbers, so the 6 nines to the power of 1,000, or 10,000. So you will have a significant amount, 10%, 15% of electrons that may be here. So this will distort your line. And the line will not be distorted in the same way if you have transferred it from the very beginning of the CCD here on the side, because you transferred it only 100 times before getting the readout, or 10,000 times. So the lines will be distorted in a different way from one edge to the other. So this will distort your IP, and this will fake you a radio velocity or a calibration error. So we tested this using Fabry-Perot's, which I changed the flux. Because what I didn't say is that this effect here is furthermore flux dependent. So the more flux you have, the better the transfer. When you are at low light level, then the probability to forget one electron is higher. That's this curve here. Okay, that's the charge transfer inefficiency, so the opposite of the efficiency, as a function of flux. And you have a peak here at low level of light flux, and then it goes down again. So that's very tricky. And we tested that on espresso by changing the flux level a lot. Okay, the noise increases, but it seems that we don't have any systematic effect here when changing the flux of the Fabry-Perot. So we illuminate with the Fabry-Perot, we measure the radial velocity of the Fabry-Perot, then we decrease the flux by a factor of 1,000, and we remeasure the radial velocity, and there seems not to be any systematic effect. Okay. Sorry? I don't know. It was probably me. Yeah, I just put it as that. It was, you know, at that level, you may have a cosmic hit, and the data reduction is not cleaning that correctly, and you may have an outlier. Okay, so the nonlinearity, sorry, I'm not talking here about nonlinearity, because the electrons are not lost, they are just transferred to the next pixel. Yes. Yes, there is nonlinearity effects. This is, for example, the so-called brighter, fatter effect, or something like that. Okay, so there is a nonlinearity which will, but this one is, for example, symmetric. But there are other effects which might introduce asymmetry. You're right. So here I'm talking just about that for the moment. When you look in all possible effects, it's scary. Okay, we did the same on a star, and indeed we get even, let's say here, we started at signal to noise 280, we went down, 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 down. So this is 1 meter per second. Okay, the noise, of course, increases at low signal to noise level, and then we went again at 280. So down to signal to noise level of 30, it seems to be okay. But this was not okay on hard snores. Here we did the same tests where we changed the signal to noise, and you see here, these data points are systematically shifted by 20 meters per second. 20 meters per second. Okay, it's at the level of the noise, but it's systematic. So if you have, and this happened on the SOFI spectrograph, they were observing at very different seeing conditions. And they had a big systematic effect depending on the seeing. So they had to fix the signal to noise ratio of the observation in order to remove this effect. So they were increasing the exposure time drastically at bad seeing conditions in order to avoid this. But this can be corrected, because if you know how many electrons go from one pixel to the next, by your recursive method, you can actually a posteriori, so after readout on the raw frame, you can bring the electrons artificially back to the previous pixel, because you know how many electrons are in this pixel, and so you know how many went from here to here, so you can bring them back from here to here. And you can correct and recover, and that's what we did with HARPS. So the red one are the non-corrected radial velocities, and the blue ones are the corrected radial velocities, where again you have much less systematics once you correct. There are so many cosmetic problems on the detector. Okay, bad columns, bright columns, fringing, these kind of things. This you all see when you do the flat fielding. When you have to do flat fielding because of this. Otherwise, your noise will be determined by the response of every pixel, which changes from pixel to pixel. So you have to flat field, spectral flat field, if you want to get rid of all this. And you have to do it at the signal to noise level, which is much higher than the signal to noise of your observation. Otherwise, you introduce additional noise by correcting it. That's a funny one. We didn't have on espresso, but we had on HARPS. When they produce CCDs, they do this by block stitching. They stitch, by photolithography, they expose one zone, then they make a step, they expose, they step, expose, and so on. So they produce a big CCD by actually illuminating several blocks here, one after the other. And if the step is not an exact multiple of the pixel, then you will get here, here, okay? Here, you get stitching errors. So certain pixel will appear smaller or larger than others. If you don't take this into account, then you get, and you do the wavelength calibration, and you get this. Okay? You suppose that the pixel number is an exact measure of the dimension, but that's not the case. The pixel number is not exact measure of the dimension, it's just a number. And since there are these blocks here, you actually make you do an error in wavelength calibration, which is of the order of the pixel size at that very location. So this curve here represents the wavelength solution determined by a laser frequency comb, where we know exactly at which distance are the different lines. So we can correct for all these effects because we know exactly the wavelengths of the laser frequency comb. And from there, we subtract the wavelengths solution determined with thorium, which are not equidistant, and we have less precision, and we get here fitting errors and polynomial because there are not enough thorium lines. In addition to that, we get here the stitching errors. And look at the scale here. Okay, that's 100 meters per second. It's systematic, but it's a lot. So this will probably not affect your repeatability too much, but your accuracy. That's one of the large teledyne detectors, 9,000 by 9,000 pixels. There are also from STA, Arizona. It's a very similar detector. These detectors have to be cooled. They have to remain at the stable temperature, but they're not. And so we tested here once at ESO, colleagues of us. What happens if you change a little bit the temperature of the control stage of the detector? And they measured using thorium lines on a raw frame, sorry. They measured the position of the lines and they were moving. So there was a breathing of the detector in one direction with respect to its fixed mechanical reference. It was breathing like that from the central point somewhere. Okay, these were a mosaic, so they were breathing in different directions. So that you would see actually on your spectrum. And in addition, it's not everywhere on the detector the same. So if you apply the same wavelength calibration from the night before and the detector has changed, you will have very crazy and weird wavelength solutions that are not applicable to what you're observing. How can we monitor all these, or at least many of these instabilities? That's a slide I prepared a long time ago to explain the difference between the iodine cell technique or self-reference, where you inject on the light path of the star an absorption cell that will superimpose here on the stellar light absorption features that you know by laboratory measurements very precisely. And then you can say, my light is affected by the same errors, my stellar light. So the stellar lines are affected by exactly the same errors as the iodine cell absorption line. And you can do some kind of deconvolution and you get a corrected spectrum. The problem of this is that it's restricted In wavelengths domain, you can use it, 500 to 600, more or less, nanometers. It is absorbing, and you need a very, very signal-to-noise level to do this pseudo deconvolution. That's why we never went for this technique here, but for the simultaneous reference technique, where we project simultaneously with the star. We have two fibers feeding the spectrograph. They produce two slightly displaced spectra. These are the orders of the star spectrum. These are the orders, in that case, of the thorium-argon lamp. And you illuminate every time you observe, either during calibration or during scientific observation, you have always this thorium lamp illuminating the second fiber. And if the instrument drifts, you will track it with this calibration source, because you know that the calibration source is stable. Okay, let us zoom, call it object fiber and reference fiber. Here we have the star, and here we'll have a thorium-argon or a Fabry-Perot later on, or any other laser frequency comb. You can do any stable source. The source must be stable between the calibration at the beginning of the night and the moment when you do the scientific observations. Because you have to be sure that what you track is the instrument drift and not the calibration source. How does this work? I tried to do a schematic here. So we measure frequently the rate velocity by cross-correlation. We make an average, all the lines, using a cross-correlation mask. Okay, so you have this mask, you move it over the spectrum, and you see where you have minimum correlations. This means that the mask is in phase with your absorption lines. But before doing that, we have to calibrate the spectrograph. Okay, so you illuminate both fibers with thorium-argon. Here, you do the correlation, you get the 0 point for fiber A at the beginning of the night. You do the calibration on the second fiber, and this defines your 0 point at the beginning of the night during calibration. Then you go during the night, you do the scientific observations. So this time you have the stellar spectrum here. You correlate your stellar mask with the object fiber spectrum. You get a radial velocity measured. But this is not necessarily the real radial velocity, because during the night the instrument might have drifted. So you check that with your fiber B, and you will see effectively the instrument has drifted a little bit, and then you determine the real radial velocity of the star is the radial velocity measured on fiber A using the calibration of the beginning of the night minus the drift measured with the fiber B. That's the concept. Any questions? You do for every observation, you have always fiber B illuminated with a reference source. Yes. And please, I know that this is commonly done. It's called simultaneous calibration. It's not a simultaneous calibration. It's a drift measurement. It's a reference technique, if you want, because the calibration of the spectrograph has been done in the beginning of the night. The only problem is that that calibration is not valid anymore. So you have to correct it by the drift you have measured. But it's not a simultaneous calibration of the spectrograph. That's a good remark. I didn't say it. The assumption here is that both spectra, both fibers, see the same instrument. If they don't, if they are very strongly separated, or if they follow a different path, then this assumption is not valid anymore. So yes, this is an assumption, and this must be carefully designed. This is a really important aspect in the design, that both spectra see the same instrument as much as possible. Sorry? Telluric lines? You can, yes, this is used sometimes, but telluric lines, I mean, the atmosphere is not fixed. Okay, you may have high altitude winds of hundreds of meters per second. Okay, stratospheric winds or things like that, or even less. So actually, you can use telluric lines like the absorption cell, like iodine cell. It's the same technique, but you just would use the telluric lines, the atmosphere. But it's you can get is between 5 to 10 meters per second RMS. We tested that on HARPS. 5 to 10 meters per second is the best. Yeah, just okay. Here, what we are measuring is in HARPS the drift of the instrument with fiber A as a function of time using the calibration source. So it's not a rate velocity drift of the star, it's just the motion of the calibration spectrum on the detector. We do it with fiber A, we do it with fiber B, the red one, and we compute the difference, and we are at the level of 10 centimeters per second in differential terms. So this means that our instrument is able to track instrument drifts at that level of precision, at least. That's with the same with espresso. Here, that's the drift over, that's one night. That, so 10, much better than 10 centimeters per second. That's the drift over several months, 180 days. So there is a drift over several months, seasonal effects, and the Fabry-Perot itself is also, but when you do the differential drift between the two fibers is less than 7 centimeters per second per day. Actually, now that it's stabilized, it's 2 centimeters per second per day. That's the more recent measurements. There are other effects. I will go very quickly through. Telluric lines, if you don't take them into account, then if you just do blindly, for example, cross correlation over the full spectrum, then you may have over the year effects of 10 meters per second. Here I removed the strongest telluric lines, and still you can have meters per second effects over the year because the star is moving, the stellar spectrum, because of Earth's velocity, but the telluric line are not. And you get huge systematic effects. You may have a non-resolved source within your fiber, a binary star, non-resolved, or just not enough resolved. And then every time the thing changes, you inject more or less of the poorly resolved companion. So you will have spectra, contamination of your target spectrum by its neighbors here. And this can produce effects of several tenths of meter per second, depending on the magnitude and the spectral type of the companion. Sky. So the moon is reflecting solar light. If you go on the website, what is the sky brightness? Oh, 21st magnitude. No problem. The problem is that there are always a little bit of cirri and thin clouds, and this changes completely the situation. That's espresso, a Rossiter-McLaughlin measured on a 12.4 magnitude star. Unfortunately, we were observing with the fiber B not using the simultaneous reference, but exposed on the sky. So we could measure the sky background, subtract it from the stellar spectrum, and correct for it. And then you get the blue curve, which is a slightly better Rossether McLaughlin. Okay, we are here photo noise dominated. But still, you see here, if you don't correct, you get this second peak. Very quickly through calibration, wavelength calibration, a problem that I mentioned. So we are here, we are starting doing progresses. We have a problem is that we used to use thorium-argon lamps for the visible. They do not exist anymore in the quality we need. They are now made out of thorium oxide instead of metallic thorium. And if you get them at all, because in the meantime, I don't know, maybe Abhijit has an internal somebody, yeah, you have some in the drawer, but at least in Europe, in the US, you don't get them anymore. And this is a problem. So we have to go to uranium lamps, which seems to be a good alternative, but the better alternative would be a laser. Calibration, concept of calibration, you determine for a known source, you determine the position of every line, okay, the pixel position, and you associate the wavelengths of every line, and you fit this relation, and you get the wavelength solution, okay? And then when you look at the star, you apply this wavelength solution to the pixel, and you get the wavelengths of the of the stellar line, which is at that pixel. That's the wavelength calibration. That's what you do at the beginning of the night. And that's what you shift during the night if your instrument drifts. I told you the thorium lines are getting sparse, but the problem is that they are not really good. Look at the lines. There is a huge dynamic range. There are narrow, there are weak lines, strong lines. They are all blended. This is not good for wavelength calibration. In addition, they age. Okay, so we would better go to a laser frequency comp, but they are extremely expensive for the moment and not yet at the reliability level we need. So we developed, and many groups did also a Fabry-Perot etalon, which produces basically the same spectrum as a laser frequency comp. There are two differences. The first, so you see here, the stellar spectrum and the Fabry-Perot spectrum. Very nice, more or less equidistant in frequency, lines which are equidistant in frequency. The problem is that the Fabry-Perot is not absolute because the spacing is given by mechanics. So you don't know exactly what is the absolute wavelength, and it can change. And the second is that the lines are not infinitely narrow. So they are not perfect for calibration, as perfect as the laser frequency comp, but they are perfect for the drift measurement. That's what I've shown before. And also, since there are so many lines, they are perfect to actually combine thorium with Fabry-Perot. The Fabry-Perot giving you the wavelength solution at high density of lines and a thorium line, even one single thorium line, which anchors you the wavelength solution in absolute terms. That's what we are doing on espresso and harps, and it seems to work well. This is a test we did during the commissioning. We took one scientific exposure, and we reduced this scientific exposure using 9 different calibration sets. And you should get here a flat rate velocity because it's always the same exposure. You're just changing the calibration set. And that's what we get, okay? It's 4 centimeters RMS. So that's the level of quality of the calibration. Is this sufficient? No, because that's what we observed with HARPS when we changed the fiber. That's the rate velocity over many years, 10 years of tau Ceti. That's the rate velocity since 2015. And there is a jump. That's the full Vizadov maximum. The focus was drifting. But fortunately, it didn't have any impact on the rate velocity. We stabilized the focus, good. But we got an offset for every star. And this offset was not the same. It depended on the rotational velocity of the star. And this is because the instrumental profile had changed. And when we do just the standard calibration, we are blind to these instrument profile changes. Because the star, so by the way, I skipped this one. When you do an instrument profile change and you convolve this with a line which is broad or with a very narrow line, okay, laser or thorium on one hand, and stellar line on the other, the shift, the net shift that you produce, it's not the same. Okay, here it's the net shift as a function of different line width of the PSF with respect to the line. And the line shift you get can change by 15 meters per second. And that's what happened. We were doing the calibration before changing the fiber with the thorium, narrow line, measuring the star, broad line. We had the systematic. But then when we changed the fiber, we changed the IPF and the systematic, the IP, and the systematic changed. And we had up to 20 meters per second offset. This is almost my last slide because I wanted to show what we do on the solar data. So that's a little bit my takeaway message in the sense that there is still a lot to do. Okay, we still do not have a reliable wavelength source, which narrow lines, absolute, which covers the full wavelength range of our spectrograph. The laser frequency comb that have these characteristics do not yet exist commercially. Even if we manage to have a laser frequency comb and to measure the instrumental profile very precisely, we still have to deconvolve the spectrum from that to get absolute velocities. And when I say absolute, it's not because I care about absolute, but because if I have an accurate measurement, I have also a repeatable measurement. If I can get rid of the instrumental profile, even if I change the instrument, I should get the same velocity measure. There is the modal noise question. There are the stellar signals to understand and to understand how to mitigate them. And one big issue here is a pure pragmatic one, is that when we move to bigger telescopes, we move to more and more expensive instruments. And this one is also to be solved, in my opinion, if we want to get to ELTs. Just to show that with data reduction and data processing, you can do many things. Here, for example, so there is a lot of information in the spectra. Here, that's a river diagram of basically a time sequence of all the spectra from which we removed the average stellar spectrum. And what you get here are residuals. I don't know, thorium lamp contamination, absorption, atmospheric absorption lines, all these things. We will all see them as residuals to the average spectrum. You can model them, you can do principal component analysis or whatever technique, and you can remove and you can clean the spectra. even before doing a time series analysis of the radial velocity that you have to do. Okay, you can even clean stellar effects with this. Okay, I'm showing that because I wanted to show our solar telescope data. That's the raw data you get out of the pipeline. And as Sourav said, okay, we are looking for a 9 centimeter per second signal in future where we have 1.43 meters RMS, which is actually quite good, but still. But once you clean the spectra, you may get that. Okay, you just blindly clean them with this technique I've shown before. And you can get signal, you can detect. So here, the RMS is 60 centimeters per second, but you can get signals as low as 30 centimeters per second here in a 1 year orbit, potentially, on this data. And with that, I stop, and I thank you for your attention. You're shocked? Questions? Sorry, can you repeat the question? The barycentric, yeah, no, but maybe I just, yes. So there is a relativistic effect. Absolutely. So yeah, I didn't talk about that. So there is, of course, at every moment of your observations, you have to know where you are on Earth and which is your barycentric velocity of the observer in the direction of the observed object. It starts to become, I mean, we are at the level of centimeters per second. Okay, if you take ephemerides, and I think we are at the level of 1-2 centimeters per second level. Yeah, at least. Yeah. You need to know the star with an accuracy of better than 1 arc second. Yeah, I guess so. Yeah. But it's a very good question. I mean, many times we were plotting the rate velocities, and every time, oh, maybe there was an error, mistake in the barycentric velocity correction. Maybe we didn't. There are a few relativistic terms that you should add or not. There is the secular acceleration. I never thought about that. Okay, for close-by stars, the radial velocity of the star changes as it passes by the Earth. And you can measure that. If you take tau Ceti, this is of the order of 1 meter per second per year. You see a trend like that. First time, oh, the instrument is drifting. So there are many of these things. Yeah. This is a very good question, and this has been debated. You remember that the fibers, especially non-circular fibers, are very good at near field scrambling, so focal plane. If you inject a point-like source into an octagonal fiber, the light will be made uniform almost perfectly. If you inject the pupil into the fiber, the pupil is already uniform. So why do you want to scramble it? Okay, but since you have guiding and seeing effects, your output pupil of the fiber will do like that all the time. So this is, if you don't have a double scrambler, I would not do that. Okay, you go with the focal plane illumination. But if you have vignetting by the dome, a little bit of vignetting, and you don't have the double scrambler, then you are dead. Then you better illuminate with the pupil. You need a scrambler anyway. Yeah, mandatory. a double scrambler. Yeah. I mean, maybe you don't agree, Sourav, but you agree. Okay. Asymmetric PSF or IP? Sorry, I have to. Okay. Yeah, thank you. Not working. Now, maybe.
So what I'm asking, okay, last one, where people asymmetricity was 1%.
Yes.
So in that one, we are achieving somewhere like 8 meter, 12 meter, or some 15 meter kind of. So my intention is here, sir, where we're talking about the PSF uniformity, it is in the cross dispersion directions and main dispersion direction, that asymmetricity, or yeah.
I was talking only of main dispersion direction. I do not care about cross dispersion direction.
Okay, so one resolution element to another resolution element, that 1% mean? What exactly that mean?
Yeah, I mean, you just, I mean, this is a completely arbitrary approach. It was just to demonstrate the effect. You take a Gaussian and you move the photocenter of the Gaussian by 1%. I mean, you make it a symmetry such that the new photocenter is 1% shifted. Okay. Something like that, okay? And in that case, just the bare shift, if you think in photocenter, is 1% of the full wizard of maximum in radial velocity. So if it's 3 kilometers per second, and you shift it by 1% by the symmetry, then you get 1% you get 30 meters per second. That's the bare shift. But this shift is not the same for a broad line or for a narrow line.
Okay, sir. And so, like espresso, it have been both main dispersion and the people's asymmetricity also they have in the spectrograph.
Pupil asymmetry.
Yeah, PSF asymmetricity.
Yeah, like, we get
in the espresso.
In
espresso design, sir.
Yes, yes. Espresso is far from being perfect in terms of IP.
Okay.
Okay, it's very good, but we are using a pupil slicer there, and we are using few small optics which introduce distortion.
Okay.
It was. I'm not happy with this. If I would change that, if I had to rebuild espresso, I would change the injection. From the relay optics from the fiber to the collimator, because we need cylindric optics, we need to produce the slices, and we need to deviate the beam. So it's very complicated, and this introduces some PSF distortion.
I will have later some discussion with you. I think I will give.
Okay. Yeah. It's probably me, I'm sorry. Can you give him the microphone? It's because there is a fan here and or the AC. It doesn't work.
So what I was asking, like some ambitious projects are going on, right? Like live project and HWO in the space base. Similarly, can we have high resolution, like highly stable spectrograph in the space near future?
Yeah,
Is it possible?
That's what I said in the very beginning. Ideally, yes, but the benefits are not as high as the costs. Because you need, at some point, it depends, of course, okay? There are some wavelengths you have to go to space. But in the, let's say in the optical, at least in the bands that we can observe from the ground, you need photons, and you can only have sufficient photons on most of the targets if you go for big telescopes. So the problem with all these projects, even live, I don't know what's the size of the telescope, but it will not be 40 meters. It will be something like a few meters, maybe. So you will have a huge interferometer. Fantastic. It's fantastic. You will get a very high spatial resolution, but you will not have a lot of photons from relatively bright targets, and even less from their planets. So yeah, that's a problem from space, is that yes, in principle, the measurement would be better because there is no atmosphere, there is no turbulence, no absorption, and so on. But you still need a big telescope for high resolution spectroscopy. And that's in space, it's not in view. I mean, yeah, very expensive. Yeah. In altitude, I don't know. Yeah, I mean, I think I would not put a 10 billion or 30 billion on a low orbit. No, I would put it in L2 or somewhere else. Yeah, that's for sure. But everything will be expensive. I think HWO is where is it foreseen to be in L2? Yeah. Not aware of that. I don't think that there is any radio velocity. This would also cost a lot of time. I'm not sure that people are ready to put a spectrograph dedicated to one target for many hours of observations or many hundreds of hours of observations. So I'm not sure this is even philosophically plausible. No, to my knowledge, there is no, for sure there is no discovery. Whether there is a detection, a radio velocity detection, not sure, I don't think so. But let me correct if nobody knows.